All right, so we are still talking about NMR. So far, we talked mostly about some theory, and last time we just started talking about chemical shifts. So let's just return to the beginning of the chemical shifts because I got a little stumped there, which was dumb. So basically, we have this applied magnetic field, the big magnet. And we said, well, if that's all that influenced the chemical shift, then all the protons should have the same chemical shift. Okay, but it isn't really the B0 here, which is the one that influences the actual chemical shift. It's something called the B local. And so this is the magnetic field created in the local environment. Notice that it's subtracted from B0, and so the B effective is what actually influences the individual shifts, okay? This B0 comes from the electrons around a nucleus. Okay, because the electrons, I was kind of leading this way last time, have the opposite charge. The magnetic field created by the electrons is opposite of the applied magnetic field. And so it creates, it essentially subtracts from, like the equation shows, subtracts from the magnetic field. So it's essentially kind of protecting or shielding a proton from the full strength of the magnetic field. Okay? So this B local can be influenced by a number of things. The one that we were talking about first was the electronegativity. Here, this is just another slide of what I was just saying that I brought in from my other class. So if we have some B0 and we have some large amount of electron density around a proton, then it's going to create a large opposing magnetic field from the electrons, and it essentially subtracts from this. And so this part right here would just be the B effective. And so this one would be shielded, and so it would move to the upfield direction. Okay, or it would be in a more upfield direction. Okay, alternatively, if there's a lower amount of electron density, then the B local is smaller. It only slightly shields the nucleus from the magnetic field, and so this would have a stronger, so remember, the stronger the magnetic field, the greater the energy gap, the higher the frequency, right? And so we see, if there's more B0, we have a higher frequency. Okay? So we were just looking at some different effects from electronegativity. And so when we have electronegative atoms, it's going to pull electron density away from the nucleus, and that's going to cause de-shielding, okay, downfield movement of the protons. So for example, I guess if we're looking at these, if we just had an alkane as a reference, right, if we had an H instead of a fluorine, then these terminal signals would be about 0.8 parts per million, okay? If we put a fluorine, most electronegative pulls a lot of electron density away from there, de-shields all the way down to 4.5, okay? The less electronegative, the less de-shielding. So these, here's the one I already had there. And so this was just a variety here, okay? Of course, these effects can be additive too. If we have, one methoxy group, it's this, that's the methyl group. But if we had So if we had the CH2 here, right, this might be a little farther downfield, let's say 3.5. But if we had a CH and we had two methoxy groups, right, then they're going to add, not in a necessarily in a linear, well, it would be probably linear, but not double 3.5 going up to 7, but this could be somewhere up around, say 5.1 or something like that. Okay? All right, so we were just starting into this, what's called diamagnetic anisotropy, and so this has to do with electron ring movements, or movements of electrons in aromatic, not only rings, but in pi systems. Right, and we know something different is taking place because what we see is that all of these signals here that are drawn out are on carbons that are sp2 hybridized. sp2 hybridized carbons are more electronegative than sp3, but not so electronegative as a fluorine or something that it would move it this far downfield. Okay, so that doesn't really fit. And if we followed the trend, if it was some electronegativity issue, we'd see a downfield shift here for the hydrogens on sp2 carbons. And what we would kind of expect is if we had an sp hybridized carbon, it should just continue the trend and be even farther downfield. But that, in fact, is not the case. The terminal protons in alkyne are more like 2.4. Okay.
So sp2 and sp are more electronegative than fluorine, or?
No, they're not. So that's the issue here. So, based upon the chemical shifts, if we were only trying to use electronegativity as the argument for the chemical shift, and we see a chemical shift for this aldehyde clear down at 9 parts per million, then it would suggest something is even more electronegative than fluorine, right? It's even further downfield. Okay, but that just doesn't fit. Okay, so the argument is this diamagnetic anisotropy, and this is kind of a hand-waving argument because I think you probably have to get into the math or something to really prove this. And I don't know, I've never been fully comfortable with it, but we just use the same explanation every time. Okay, so this is the way it goes. So we have our applied magnetic field, and if we have benzene, the benzene can orient itself perpendicular to the applied magnetic field. If it does that, it induces the movement of the electrons around the circle, because remember in benzene we essentially have, because we have p orbitals all the way around, we essentially have kind of like a donut of a pi system, right? Or the molecular orbital, the lowest molecular orbital is like this, is kind of like a donut. And so it's going to induce a movement of the pi electrons. And that in turn creates a magnetic field. It has these magnetic field lines. You've probably seen magnetic field lines like drawn on the Earth or something like that. It has these magnetic field lines, and notice here, so here's the induced magnetic field from the movement of the electrons is moving around like this, all the way around. And the important part is that around the position of where the proton is, these magnetic field lines are aligned with B0. Okay, so this magnetic field line here is aligned with this, and so it's going to essentially add on to the applied magnetic field, creating, a B effective that's even bigger and causing a downfield shift. Okay. it says it down here. Okay? So this is an argument why, benzene would have such, farther downfield signal. We can do a similar thing, which is drawn for just isolated alkenes and aldehydes. I'm not quite sure how they're supposed to cycle here, but again, they generate these magnetic field lines, and just like with benzene, in the position where the protons are located on both sides here, this magnetic field is aligned with B0. So again, this is going to cause a downfield shift, okay, more than what we would expect otherwise.
Is it correct to say whenever we have sp2 or sp, we have anisotropy?
Yeah, I think so. Yeah. So with the SP system, because it doesn't really follow the same trend, it's a little bit of a different situation, a different orientation, because for SP, for an alkyne, we have two pi orbitals that are perpendicular to one another, right? And so we almost have a donut that goes around the axis of the alkyne. Okay, so we can have cycling this way, which creates these magnetic field lines. But what's different here is now that we look at the location of the hydrogen, and is in a location where the magnetic field lines are opposed to the applied magnetic field. Okay, so it's going to actually cause a little bit of shielding rather than de-shielding.
That does feel that maybe.
Yes. Yeah, it seems like by now that even for just this level, they could probably come up with a better argument. All right, but we'll stick with it for now. So here's just some general ranges. In fact, I always say that, you can do maybe 80% of the spectroscopy problems just by knowing some general ranges of chemical shift, and then if you have some that don't fit, or they aren't simple like this, then you can, do something more. Okay, so we have this range, like above 9 parts per million, up to maybe 11 or 12 here are the aldehydes and the carboxylic acids. We can usually tell these apart because the aldehyde protons are usually very sharp, and the carboxylic acid protons are usually broad from hydrogen bonding. Okay, once you start hydrogen bonding, you kind of have a variety of electron densities because the bond lengths can be varying, and so you also have exchange, which causes a broadening of the peaks. So this is H bonding and chemical exchange causes the broadening. Okay? So usually in this range of about 8 to maybe 6.5, let's just go all the way down here to 4.5, are the hydrogens that are attached to sp2 hybridized carbons. The benzene system protons are usually a little bit further downfield, but not always of just normal vinylic protons. It just depends oftentimes what groups are attached. Okay? And in fact, aromatics, especially if you have heteroaromatics, pyridines and indoles and things like this, they can go down beyond 8 as well. Okay? In this middle range are usually protons are on atoms that have an electronegative atom on them, and these are what we looked at first. Their position within this range depends upon how electronegative that group is. So, if it's an oxygen, it's going to be more on the downfield side here. If it's nitrogen or a weaker halogen, it might be on the upfield side. Okay? In the 1.5 or maybe 1.7 to 2.5 are usually protons that are adjacent to a pi bond. Okay, on the downfield side of this are usually the ones that are next to carbonyl group, and on the upper side of this are usually the allylic ones, like this one here, next to just an alkene. Okay.
What about sp carbons? Where are they in this?
The sp, the protons on the sp, well, we said that they were like around 2.4 or something, so they would be somewhere in here. And then the same added effects, right? We talked about, if we have more substitution, they're going to be more on the downfield side, less substitution, methyl versus methylene versus methine. They move downfield, and so all of those things are additive too. And so also up here are the saturated ones, usually about, 0.8 for methyl groups, up to 1.5 or so if they're more substituted. If we have some things like cyclopropanes can be way upfield, in the 0.3 or 0.2 or something like that. And all of these have. All right, so our book has a bunch of tables, and these tables are what we used back when I was taking these classes. But we might as well just quickly look at what these are. So there's some tables like this where they're just looking at some group attached to a functional group. So this M here can either be a methyl or a methylene or a methine. So if that group is, attached to, if it's just attached to an alkyl group, then these are just the signals here for an alkane, essentially. So, the line, the bar is a methyl, the two circles are a methylene, and the two dots are a methine. So what we see is in all of these, it always goes methyl is more upfield, methylene, methine, right? Just a substitution difference here. But if instead, say, we have a chlorine, so this would be just chloromethane if it was the methyl, or chloroethane if it was a CH2 or something like that. Then it's moved down to here. Fluorine is here. Some other ones. If it has an alcohol, methanol, here's the 3. So we just read them straight off like that. Okay. There's another table that is a kind of a beta effect if it's the next carbon away. So it's separated by a carbon. So here we have either methyl, methylene or methine, and if the functional group is 2 carbons away, here methyl carbon and then CH2, then these are the chemical shifts. So these inductive effects, do have an effect over more than one position, but the effect drops, the impact drops as it gets farther away. Now there's also these tables, and I think this is essentially what the NMR prediction programs do, is they calculate these tables, or similar ones. And these were called Schuler's rules. And they're just, empirical rules. So they just made up a database. They looked at tons of compounds, and they just fit these. So the way that it works is if, in this case, is that too small to see? Can you guys see those? If we have a CH2 between 2 functional groups or a CH between 3 functional groups, then we have a starting point. The CH2, we essentially start for what would be the chemical shift of methane. And they set that at 0.23 parts per million. And then we have these substituent constants that we add for each of the groups. So for example, here they have, I didn't make up any other ones. Here they have just this bromomethylbenzene, like this. So we'd be calculating the chemical shift for the 2 protons on this carbon right here. So we start with 0.23. We have a bromine on one side. We look down on the list, and I can't even, it's blocked by that thing. Oops.
It's in 2A.
2A, is that the same? 1.53, but I think
Oh, but they have
2.33. I think, yeah, maybe it's down there. Now they don't even have it on 1A for alkyl methylene protons, or substituting for methine. So they have different ones for those two. So I'm not quite sure. Maybe I chopped it off and didn't fit it all in there. So they add 2.33 for the bromine. For the phenyl group, it's right here, 1.8. They put 1.85 up there. It says 1.83 down here. So I don't know why that is. But essentially they add these up, comes up with 4.41, and then they say, oh, the actual value is 4.43. So it came pretty close. They do a similar thing over here. You know, if we have a methine, you just do the same kind of thing. You start with, what are they starting with over there, though? Huh. Okay. I thought you still just started with the same thing, but they're starting actually with 2.5. Oh, I don't know. I'd have to look that back up. Yeah, I thought that they'd started with 0.23 again, but they didn't. They started with 2.5. So it's a similar thing. I'd have to read through. They got all the direction stuff, and we're probably not going to really do this. You know, when I very first started teaching this class, we used to do a bunch of calculations like this, but we don't really need to do that anymore. And we'll look at a program that Andrew said he uses a lot already to help kind of predict chemical shifts and things like that. Okay, you can do the same thing with alkenes. For the alkenes, whether the group, so here they have this proton, and you're going to, the chemical shift is going to be impacted by whatever substituents are on these other 3 positions. And in this case, it's important whether that functional group is either on the same carbon, geminal, or trans, or cis. So for any of these different groups, let's say we have a carbonyl that's conjugated, so it has a different effect. If it's on the same carbon, it's 1.06. If it's cis, 1.01. If it's trans, 0.95. So it just depends on where it is. Okay? And some of the interesting ones here, I think, is if we have something like, I thought that one would be one of the interesting ones, but that doesn't have that much difference. If we have, well, we can look at one of these others. Where's that methoxy or something? Oh, so let's say if we have a methoxy group or something like that, then notice that if it's geminal, it shifts it downfield by 1.18, but if it's on the other end of the position, so if we have something like this, this carbon here would be 1.1 downfield, but at the other end, these are like minus 1.0 to 1.2, depending on its cis or trans. Okay, and so why is the difference there?
The place that they are may have different effects.
Right, it does, obviously, right? Because we have it's like 2 parts per million difference, right? In one case, it's going downfield 1, the other place is going upfield 1.
Is it because the oxygen shifts the applied magnetic field of the alkene up more, so that there's more of an effect of that field on the geminal carbon as opposed to the opposite?
Well, kind of. I think for one thing that we can see is that somehow that methoxy group is creating a very polarized bond, right? So it has to be on the carbon here. If this is shifting it downfield, this is going to be de-shielding. And this other end here is going to cause more shielding, at least relative, right? Right, so how would that methoxy, so we can, I think maybe it's intuitive from what we've talked about already that this geminal one, if we have an oxygen, it's more electronegative, it's just going to pull electron density away from that position, causing de-shielding. Okay, but how does it affect the other carbon, causing the other position to be shielded? What if I draw in some non-bonding electrons on here? Does that...
Is it resonance?
Resonance. So we can have resonance so that these electrons can be donated here. That's going to push these electrons over here. And so we have a resonance structure that looks like this, plus here, minus over here, right? And so this is going to cause shielding, right? A greater electron density at that position. Okay, another type of situation that we could have if we have a double bond, let's say we have a carbonyl right here. Okay, this is another situation where the protons that are attached to this can have very different chemical shifts. And again, it can be based upon resonance that this can pull electron density towards the oxygen. This causes de-shielding here, especially at that position, right? Because we're going to end up with a delta plus at this position. Okay? All right. Let's take a moment. I'm going to pause this, and I'm just going to show you that program. Yeah?
With the middle example, I guess the bottom two, because it's the same.
Yeah?
Does the electronegativity of oxygen not matter as much as the resonance when it comes to predicting the...
Well, I think... with oxygen, in a lot of these cases, it can do two different things, right? It can pull electron density away inductively, or it can donate if it can possibly have resonance. So, if we look at these two resonance forms, definitely the one in the middle, this one's going to be more stable. This is a predominant one. But because of these non-bonding electrons, those electrons can be shared, right? So even if this is minor resonance form, it does show that there's some buildup of electron density at this position, right? Which is, I think, an explanation, but also perhaps a demonstration of the difference in electron density, right? Okay, so let's, what else do we have? Okay, so let's The next thing we're going to talk about is chemical shift equivalence, which is essentially how do we predict how many signals we should see for a given structure. Okay, so it's a matter of identifying symmetry mostly. Okay, so nuclei will be shift equivalent, so they'll have the same chemical shift if they are interchangeable through symmetry or some rapid chemical process. Okay? And so some of the different ways that they could be interchanged here at this top one is if they can be interchanged by rotation around an axis. So if we put through this molecule, if we put an axis right down through the middle here, we could rotate this by 180 degrees. Okay, so this would be, I think, a C2 axis. And so these two protons, if we rotate it around, those two protons would interchange positions, right? So okay, so shift equivalent. The next one, because we've exchanged one of those chlorines for a bromine, we don't have a rotational axis anymore. However, we can have a plane of symmetry that goes down through here. Because this tetrahedral, it would go right through the two. Well, we wouldn't want to do it that way. In fact, we'd want to do it this other way here, right through the middle, right between the two hydrogens. And they would bisect the chlorine and the bromine, right? So these two would reflect each other through this plane of symmetry, and so they would also be shift equivalent. Okay? And the last type of symmetry is a center of symmetry. So in this case, it's all going through a center here. So these two hydrogens, for example, reflect each other through this center. These two reflect through the center, and notice the chlorines are in the same position relative to that center as are the fluorines. Okay, so this is a little less common, though. Okay, so the other way that we can do this is through kind of a substitution process. So if we have a molecule like this, what we would do is we would go through a process, a two-step process, where we would take one of these and substitute it for some other group. So the most common is just you could use anything really, but we'll substitute it for a deuterium. Okay, so we could go like this. We'd put a deuterium here and a hydrogen here. Then we do it the same thing to the opposite position. So now the deuterium is in back. Hydrogen is in front, and we'd ask ourselves, what is the relationship between these two? They're the same, right? Because we can just rotate it around that axis, superimpose it right on top of the other one. So that means that those two protons, the protons are called homotopic, okay? And that means that they are going to have the same chemical shift. They're equivalent, okay? Let's do the same thing for this next one. So we're going to replace this one with a deuterium. Then we're going to replace the other one with a deuterium. Like this. And again, we ask ourselves, what is the relationship between those two compounds?
sigma v.
Yeah, it's reflected.
Are they superimposable? Are they the same though?
Yeah.
They're not superimposable.
So what do we call them relative to one another?
I mean,
Heterotopic?
I mean enantiomers.
They're enantiomers, right? They're mirror images that are non-superimposable, right? So they are enantiomers. And so the protons are called enantiotopic. Okay? Enantiotopic protons will be equivalent to one another as long as they're in an achiral environment. Okay? So these are going to have the same chemical shift in an achiral.
What am I chiral environment?
Yeah, so that means that if they're just in a normal solvent or something like that, they're going to have the same chemical shift. But of course, if you had something where you had enantiotopic protons, perhaps on this molecule, not something so simple as this, but it was, say, binding into a protein pocket, right? Those two protons could have different,
Orientation.
and be arranged towards different groups, and so they could react differently. In fact, I think people have done, if you ran an NMR spectrum of a compound with enantiotopic protons in a chiral NMR solvent, then they could have different chemical shifts as well. If they're going to orient in some preferential way with the solvent, hydrogen bonding or whatever, they could have different chemical shifts.
So if you just lock the environment in a certain orientation, then you could just...
Yeah, I don't know if it has to be fully locked, but if there's some preference or something, it creates a different environment for one proton over the other, right? But because they're enantiotopic, it implies that they have a mirror image relationship to one another, right? And so you have to have something where one side of the mirror would end up different than the other side. Okay? So what about this one down here? We're going to talk about these two protons here. All right, so we're going to do the same thing. So I'm going to put this one deuterium H, and then I'm going to keep this the same. This one's going to be a D and an H. So what's the relationship between those two compounds?
They are enantiomers again. No, they're not. They're not. There's no. There wouldn't be a mirror plane because you have the chiral.
They are chiral, so are the ones above them are chiral.
Yeah, but they're not mirror images of each other.
They're not mirror images, so what are they? Diastereomers. Oops. So what do you think you call the protons? Diastereotopic. And what do you think? Are they going to be the same or different? Different. Diastereotopic protons are non-equivalent. Okay, non-equivalent. So they should have different chemical shifts. Okay, different chemical shifts. But, in all cases, they could have different chemical shifts, but those chemical shifts could be so close that we can't tell that they're different, right? They could be...
Even with the high sense to magnetic field, we can distinguish.
Maybe it just depends. They could be coincidentally very close in chemical shift. Certainly, the higher the magnetic field, the better chance you have to resolve them, but they could still overlap, right? Just because they're diastereotopic and they have different chemical shifts does not mean they're always going to be resolved from one another, right? From a practical point of view.
But as you go to infinity.
Right,
Yeah.
right. Okay, so the other thing that, and this ended up, when I was looking at it, not really the best slide for what I was maybe trying to show here, but so chemical exchange processes can also affect what we see in the spectrum. So in this case, what we have are two equilibrating molecules. Okay, and so this is going from the keto form to the enol. So this is a tautomerization. So it's in equilibrium, and what we see depends a lot on how rapidly this would take place. Okay, in this case, this is going relatively slow, what we'd say on the NMR time scale. So, and the NMR time scale is kind of how fast we can sample it. Okay, so what we can actually see is we can see both of these compounds. All right, so here, down here, we have the chemical shift for the enol form. So that's the bottom one. And here we have for the ketone form. So this is a CH2 group, and so it's further upfield than the enol, where that proton is essentially on a double bond. Okay? And so, in fact, in this case, we could integrate these two peaks to give us the relative amounts of those two forms. Okay? Now, for example, if we heated this sample up and the equilibration happened faster and faster, what would generally happen is those peaks would start to broaden out as it goes faster, and then they would almost lose them into the baseline, and then we would probably get a peak that was sharpened up, which would be the average between those two. So if it happens very fast on the NMR time scale, all we see is an average signal. Okay? But in this case, it's slow. So if it's very fast on NMR time scale, we see an average signal. And in fact, for chemical processes, exchanges or rotations or things like this, you can calculate the energy barrier for that process by how the peaks behave as you increase the temperature. Okay, where it flattens out and goes to a single peak. So other places where it's important, so let's look at these three molecules. So in this case, so this is just dimethylformamide, DMF, common polar aprotic solvent. One of those ones that's not so easy to get rid of. So do you know what the NMR spectrum looks like?
It depends on the temperature, right? Because it's an amide bond.
Right.
But no, I don't. No, I don't, because I completely remove all of the DMF when I run an NMR.
Right.
But no, there should be there are two different signals for the methyls, and then there's one. I mean, you don't really care about the
Right.
aldehyde one.
Yeah, the
There are-
formamide one. Yeah.
But there are two distinct.
Okay.
Methyl.
Right. So here, if we had free rotation, then we should get a single signal. right? But in fact, for DMF, these two methyl groups have different chemical shifts because, there's this resonance here, for all amide bonds. Okay, which hinders the rotation. So in fact, this amide carbon is sp2 hybridized rather than sp3, and it's all lying in a plane. Okay, so those two methyl groups have different chemical shifts. So we have a slow interconversion in this case. Okay, so for cyclohexanes, go ahead, John.
For the slow interconversion, is basically if the T1 doesn't relax all the way, kind of thing?
No, I don't think it has to do with the T1. So it's not a relaxation process. Well, I guess it has to. I guess the lifetime has to be longer than the T1. And it has to be longer than, this NMR time scale. It's not really the sampling rate, but I think it's the time period between the points that you're measuring. But I think the interconversion, it's not so much about the relaxation as the sampling rate. Okay, so we'll see in maybe a little bit more later, but when we have a cyclohexane, right, we have an axial position and an equatorial position, and those positions can have different chemical shifts. Okay? However, if we have some system where this can do ring flips, right? So if this ring flips at a fast rate, then we would have a single signal for those. So for cyclohexane itself, you would just have a single proton signal. All right. However, if we put some large group on here,
So slower probably.
yeah, or you really favored one chair conformation versus the other, let's put something, the classic is to put some like tert-butyl group on here or something. But if we put something else on here as well to cause some differences in chemical shift, like an OH or something, then these protons would maybe quite different. Okay, not only because we have this OH, but also because axial is different than equatorial. Axial protons are usually more upfield than equatorial. Okay. On this molecule down here, we have a chiral center. And so oftentimes if we're adjacent to a chiral center, then the protons can be diastereotopic. However, if we have a methyl group here, then this can just rotate around like a propeller fast enough that those would all be equivalent. Okay, so methyl groups really are never diastereotopic. Well, one can be diastereotopic from another methyl group, two of them, but within the protons of a methyl group, we have fast rotation. Okay? All right. So we looked at kind of some of these type of examples already. We're just going to look a little bit at their, I didn't do that other one. Differences in chemical shifts. So for one, if we have a methyl on an ether versus an ester, then those, even though they have oxygens attached, those two have different chemical shifts. Okay, so which one do you think would be more downfield just by looking at structure than the other, right? So they're both going to have some dipole pulling electron density away.
Well, I think it's more stronger.
The which one's stronger?
The ester.
The ester. Why?
Is it resonance?
because of resonance, right? Because this one has a resonance form like this. So with the plus, I think it's even more strongly electron withdrawing. Okay, and so for an ether, this is usually about 3.2 parts per million. For an ester, it's like at 3.6. So I mentioned this, I think, early on, that sometimes if you have a system, for example, that was something like this and CH3, and there was some reason that you needed to tell which proton was which, these two would have very similar chemical shifts, whether it's an OH or a methoxy group. However, if you convert this position to an ester, then we'd see this signal would shift. This one would stay mostly the same. All right, and so that can allow you to assign which of these protons is which, because one's going to stay the same, one's going to move. Okay, so chemical way to do it. All right, so these other ones, we kind of talked about these already. If we have an ether like this, is an enol ether, then the one that is alpha to it is more downfield because of some inductive effect. The beta one is shifted upfield because of resonance. Okay? If we have a carbonyl, it's the opposite situation, right? Because the carbonyl, this one's going to have resonance going this way. This one is going to have resonance going this way. So now the beta position is more downfield than the alpha one position. Okay, so these are two cases where we really see the protons can be well resolved from one another. Similar things in benzene type of systems. If we have a phenol like this can donate electrons into the ring. So this can build up higher electron density at the ortho and the para positions. And so the ortho and the para are more upfield. They're more shielded than the meta position. Okay, because we end up with a delta minus there and here. If we have a carbonyl, it goes the opposite direction. So we should have a delta plus here and a delta plus here, right? So these are like 7.81 and 7.66. Those are more de-shielded, and this is at 7.52. Okay, so they kind of swap positions in these two situations.
So with the middle example,
Yep.
bottom example, there's a partial positive on the ortho and para position.
Mm-hmm.
Why on the ortho? Because wouldn't the double bond just change sides and it'd be the same environment for that carbon?
Which one, the right or the left? On the bottom, you mean?
Yeah.
This bottom one. Okay, so if we just did what I showed here, we'd end up with a resonance that looked like this. And these all have H's, of course, with a plus right here. Right, this is H. Okay, but from there, we can draw more resonance. We can move this electron over like this pair.
Kind of like stepwise. Okay.
Yeah. And so in a benzene with an electron withdrawing group, we have, this plus is going to be spread from here to here to here. So it's actually going to be equally, well, not necessarily equally, it'll be equally spread between the two ortho positions, and it'll be shared with para position as well.
Okay.
Yeah. Same with the left one, we got to put the minus charge on the ortho position, but then we can draw another resonance that goes to the para position, another resonance back to the other ortho position, right? Another resonance back out onto the oxygen.
Okay. Great.
Okay. All right. So we can just start kind of an introduction into this. Next thing that we're going to talk about is the spin-spin coupling. Okay? And so these are through bond influences where the spins of one proton or one nucleus can affect the other observed signals. Okay? One thing that's very important is that this only occurs between magnetically unique or non-equivalent nuclei. So if we have two protons, for example, that are related by symmetry, they will not split each other, right? Because they're equivalent. You can't split yourself. We're going to look at a number of different situations. This first one we're going to save mostly for when we go to talking about C13 NMR, but we can have one bond couplings. So this would usually be a situation where we'd have a proton splitting a C13, right? And the carbon being split by the protons that are directly attached. We don't really have any proton-proton coupling that's a similar situation. The most common for proton NMR are, these aren't the most common. We can have two-bond couplings. Okay, so these are going to be geminal protons, so this protons on the same carbon, and this can really only happen if those two are non-equivalent. So in order to be non-equivalent, they have to be diastereotopic. So it means we have to have some type of chiral center in the molecule to make them diastereotopic. Okay? The most common are the three-bond or the vicinal couplings. Okay, those are protons on adjacent carbon, so 1, 2, 3 bonds away. And then we can have more than 3 bonds, which we can kind of lump into long-range couplings. And these can be like allylic, or they can be in benzene rings, or things like that. Okay, so what we're going to do, we're going to first go through kind of the cause of the coupling. We're going to look at different peak combinations. And so these are all going to be kind of what we could say the ideal situations, which we don't always see in real spectra. Okay, so then we're going to go on and talk about second-order effects. So these effects can distort the coupling patterns from ideal. And then we'll talk about the different types of and magnitudes of the coupling constants. Okay? So let's just start into the first one here.
It's not a very important question. All right, guys, 2 slides ago.
Oh. Okay, so we're going to look at 2 different protons, and we're going to see how one proton is affected by the other proton. Okay, so let's start out by drawing. This is going to be our applied magnetic field, B0. Let's say we're going to observe this proton that's in red. Okay? The blue proton is on the adjacent carbon, so this would be in a vicinal situation, a 3-bond. And we know that this proton, the blue proton, can either be aligned with the magnetic field or it can be opposed to the magnetic field. Okay? We know there's a tiny amount more that is aligned with the magnetic field than opposed. Okay? But in this case, we're just looking at the peak heights, and so they're going to roughly look to be 1-to-1. Okay? Because the excess of the plus 1/2 is very small. Okay? So, if we were in the absence of any coupling, let's say that this red proton would just have a singlet right here. Okay? Now, some of it, half of it, is going to be influenced by this proton that's aligned with the magnetic field. So this one over here essentially has the B0 with the spin from the adjacent proton added to it, and this is going to increase the B effective, essentially. Okay? And that is going to increase the energy gap. It's going to increase the frequency at which that percentage of the protons will resonate at. So some of this is going to shift to a higher frequency. Okay, the other half, here's the B0, is going to have this B local being against it, right? So this is going to subtract from the magnetic field, and so we're going to see some of this shifting to a lower frequency. So this goes to higher frequency, this goes to lower frequency. Okay, and so this would go to here. Okay, so instead of one peak, we see two peaks, which we call a doublet. Okay, notice that there's only one adjacent proton. Okay, and so the number here, let's say down here, the number of adjacent H's, we're going to call this as N. Here, N equals 1. And our rule kind of is going to be N plus 1 equals the number of peaks. Okay? In fact, it's actually, what is it? It's actually 2N I plus 1.
What is I?
I is the the quantum spin. It's the spin, right? So for proton NMR, protons have a spin of 1/2. So in this case, 1/2 times 2 equals 1, and we can just leave that out. Okay, but if we go to another spin, that's not spin 1/2, then we have to take that into account.
And those peaks have the same height, or?
They are, yes. They would have, I guess, technically have a difference in height relative to the difference of populations of the plus 1/2 and minus 1/2 spins, but those are so similar that we roughly see this as a 1-to-1 ratio. Okay. Okay, so let's just finish this. The distance between these two is the coupling constant, and it's usually referred to as J, and that J value is in hertz. So we don't do this in part per million because remember that this coupling constant is independent of magnetic field strength, right? If we did it in parts per million, then the coupling constant would change in different, field strengths. But if we do it in hertz, it's the same. Okay? So we have this rule n plus 1. So we had one adjacent proton. 1 plus 1 equals 2. We get a doublet. Okay? The other proton over here, the blue one as well, would start out as a singlet with no coupling. It would also be split by the red proton into a doublet. Okay, and this J over here, these two, this one and this one, would match. Okay, both protons that are coupling to each other have the same coupling constant. All right? At least within experimental error. And we can talk about a reason why they don't always match exactly if you measure them. All right? Okay, so we'll go through some more of this, and we'll go through some more complicated coupling and stuff, but that's where we're at for now. All right? Yeah.
Question on the last slide.
Okay.
The